All right, let's look at this problem called Reconstruct Itinerary. So you're given a list of tickets. Ticket represent starting airport and ending airport. And you're given a list of tickets. It's for a single person. And you're also given the starting station, the starting airport. So you started from JFK. You have to reconstruct the itinerary in the order and return it. So for example, in this case, from these tickets, you can create a directed graph, and you know JFK is a starting point, so you just traverse and you go to HSC, and this is quite clear. Uh, there is one more condition that is given, which is if there are multiple itineraries, you should return the itinerary that has the smallest lexical order when it is a single string. So let's understand that in the second example. So in the second example, you can create two itineraries. One is you go from JFK to SFO, SFO to ATL, ATL to JFK, JFK to ATL, and ATL to SFO. So basically from JFK, you either go to SFO or you go to ATL. Both are giving a valid itinerary, but in this case, because ATL is smaller, so you would prefer this one. You have to handle this as well. So how do you handle this? So the simple way to handle this, when you represent this graph in adjacency list, like for example here, for each node, when you are adding the neighbors, you add those neighbors in sorted order, and you can use a priority queue for that. So when you look at JFK, you see a ticket from JFK to SFO, you see another ticket from JFK to ATL. So let's say first you encounter this JFK to SFO. So you add this in the priority queue, and then when you add ATL, because it's priority queue, the first element which will give you will be the smallest one. So that is a bit to handle the lexical order. But just lexical order is not sufficient. So what I mean by that is look at this example. Now here, let's say a starting airport is given as A. So yes, you can go from A to B, but then you're stuck, right? So yes, you want to give preference to B, but that doesn't necessarily mean that that will give you the right itinerary. Here in this case, the only valid itinerary is you go from A to C, from C back to A, and then from A to B. So yes, you want to give priority to lexical order, but that doesn't necessarily mean that will give you the right itinerary. So you have to consider both factors. Yeah? I want to give priority to lexical order, and I want to form a valid itinerary. So let's look at an example to sort of understand how to solve this. So I want to take example of this example. So first of all, let's try to understand, let's say these are the different tickets, these are different graphs that are given to us. And we have to find a valid itinerary. So we have to find a valid path that uses each ticket once and only once. And the ticket here is edge, right? So it sort of forms a directed graph which has a Eulerian path. That's what it really means. So let's first understand what Eulerian path is. So let's write out the in degrees and out degrees for each of every node. In degrees is essentially the number of edges coming into the node, and out degrees the number of edges going out the node. So let's look at A. And here, for example, let's assume A is a starting table that is given to us. So from A, how many edges are coming in? Just one. How many edges are going out? You can see there are two, right? For B, how many edges are coming in? You can see for B, there are two edges coming in and one edge going out. For C, you can look at there are four total edges. Two are coming in and two are coming out. And same is the case for D. There are one, two, three, four, two coming in and two coming out. And then for E, there is one coming in and one coming out. Now we don't have to really look at this. It is already given to us that this a valid itinerary does exist, but it sort of proves. So in a directed graph, a valid Euclidean path exists in two cases. One, either all the nodes have their in degree and out degree equal. In this case, that's not the case. For C, D, and E, their in degree and out degree are same, but for not for A and B. So that's the other condition. If all the nodes have equal in degree and out degree, then you even have a Euclidean cycle. But for a Euclidean path, you either have a Euclidean cycle or you have all nodes except two nodes which have in degree and out degree equal. So C, D, and E have in degree and out degree equal. A and B have exactly one difference in their in degree and out degree. And in A, the out degree is more, and in B, the in degree is more. This tells you there will be a Euclidean path which starts from A because this is an extra out degree, right? So there is one path going out extra. And for B, there is one path coming in extra. So A will be the starting point, B will be the ending point, and C and D will be the middle ones. So that is the strategy. Now, we want to sort of also build what you say is the adjacency list. Let's also build out the adjacency list presentation, right? So you have your A, B, okay, and you want to follow the lexical order. So from A, what all nodes you can go to? You see there are A has an out degree of 2, so you can go to B and D. You put it in sorted order, so B and D. From B, you can go to C. From C, you can go to A and D, give preference to A. From D, you can go to B and E, give preference to B. From E, you can go to C. So that is your adjacency list representation of the graph. Now what do? We start from A, okay? So we go A, and we keep following this lexical order. So from A, you go to first guy, which is B. So you remove this because you have traversed this, and so you go to B. From B, you will go to C. So you remove this C. From C, you go to A. You remove this A. From A, you go to D. You remove this D. From D, you go to B. So you have been giving preference to lexical order so far, and you are not stuck yet. It's all good. From D, you go to B, and at B you are stuck. All the edges have not been completed, but you are stuck. So how do you handle it at this point? So this traversal sort of tells you where you are stuck is your ending point. So now let's call this as the final itinerary, and in your final itinerary, B is the one that will be the last to reach. And now from D, you went to B. So what you do is, okay, B I know is the last guy. Let's remove B and let's continue. So from D, you can further go to E. Okay, so let's do this. So from D now, I go to E. From E, I go to C. From E, I go to C. And from C, you go to D. And now at D, there is nothing else. So now that means this is the last most node. So now in front of D, basically what you can do is now because everything is empty, you can just put the entire this bit here because from D to B there's already a path, right? That essentially means that your final path would be you add this D here, then you go to C and you do the same thing again. So now C, you see if there is any further paths that you could look at. There are none here, so you go C. Then you would look at E and you would see there is any further paths to go at E here. There isn't. So you and that is how you sort of build. So from E, then you add D, then you add A, then you add C, then you add B, and then you add your A. And so that's your final path. From A, B, C, you go back to A, then you go to D, then you go to E, C, D, and then B, and that's your final path. So that's the bit, right? So how do you write the code for it? So essentially, first you create this adjacency list with the priority queue. Then you start from A till you get stuck. You keep traversing. When you get stuck, the guy where you guys stuck is the last guy, and then you continue. Remove that guy, and then you continue. Again, when you get stuck, that is your second last guy. Again, when you get to that's the third last guy, and so on and so forth. Right? Let's build out a code for this. Okay. So the first things first, you want to build an adjacency list. So it's a hash map. The key is the airport name, and we are using a priority queue to prefer the lexical order. So we use a priority queue. Let's call it adjacency list. What else? What else do we have? Uh, let's maintain a linked list of string, which is our final itinerary. Let's call it route. And as you saw here, we are sort of maintaining a stack, right? And we got back, we removed that, we added it here, and then we continued further. So for that, let's maintain a stack. Right? And let's first build the adjacency list. How do we build the adjacency list? So for each ticket, so for each ticket, for each ticket uh, in tickets, source is ticket.get 0 and destination is 1. So if adjacency list does not contain the key for source, then you first add this dot put. Okay, so now you are guaranteed that adjacency list dot get source will give you uh, a priority queue. In that priority queue, you add this destination, right? So your list is complete. Now what do you do? In the stack, we know the starting point is JFK. That's given to us. The first guy is always JFK. So you add JFK. And now, while your stack is not empty, keep on just traversing. And at some point, you might get stuck, and we'll handle that. When you get stuck is when you take the first, the topmost element from the stack and then continue, right? So okay, let's call it last, right? So if, or rather while, not while, okay. So how do we handle this? Let's do int last equals to if last, well, if you're stuck, how do you know if you're stuck, right? So you're stuck if you're not present. So this is dot contains key. If you don't even present content key or the list is empty, let dot get last dot. Either the key is not present, if it's present, then it's empty. In this case, what do you do? Well, in this case, you do stack dot. So you take this element out of the stack and out, so route dot. You add it in the route, okay, the top. So you add stuff dot. You can also do like, so you take it out and then you add it, right? That is good. And if that's not the case, then what do you do? And it's simple. You do stack.push. What do you push in the stack? So you want to remove the edge, right? We were removing the edge. So now we're looking at, so for example, from J, for example, from here, from A you went, so you push A into the stack. Now from A, you want to push B into the stack, but you also want to remove this edge, right? So what you do is you do again. This is a string adjacency list of cat. You remove it and then you add it here. And that is it. And again, obviously stack won't be empty. So you'll either remove it or you push it, right? And that's it. And so at the end of the day, we do return loop. Okay, let's run. Fix a compilation error. It's a runtime error. Okay. If adjacency list contains key, okay, it's not it's or. All right, accept it, submit, and it gets accepted. So that's it. We can talk about time complexity. Clearly, it's just the number of edges. So time complexity is just OOP. Space complexity, how much elements can be there in a stack, it's OOP. So both time and space complexity is OOP. All right.